Collision theory and the energy profile of a reaction. Now that we have a conceptual overview of the collision theory, we will now look at how this relates to the energetics associated with a reaction.
We plot the potential energy or the enthalpy on the y-axis, and we plot the reaction pathway or the reaction coordinate on the x-axis. Here you see we have the reactants. Now as the chlorine atom comes in, it gets in and you're starting to form that bond and you're starting to break. The other thing that has to happen is you have to break the Cl N bond. So you go through. As this goes on, first it costs energy because you're trying to shove it into a very uncomfortable position. And now, so here you have a half-formed Cl-Cl bond, and you have a half-broken Cl-N bond. Okay. And in this case, at some point you reach a maximum in energy. Now this maximum in energy is referred to as the transition state. And the energy required to form the transition state acts as a sort of energy barrier, doesn't it? From the reactant. It's called the activation energy. Note that no matter whether the reaction is endothermic, exothermic, the activation energy is always going to be positive because it's always an energetic cost to start breaking those bonds in the molecule. Otherwise, we'll always have product. So what does that have to do with the rates of reaction? So, what we go back to is the probability distribution as a function of energy for molecules at a certain temperature T1. Let's think about this. What we said before was that only if there's enough kinetic energy would the molecules react. Now, one of the key points from chapter 5 is that not all molecules have the same energy. Some have a lot more than others. And if those molecules, even in the molecules where there's not enough energy, some of them would have an energy greater than the activation energy. So I've shaded here the proportion of molecules with energy greater than the activation energy. And it's only with those molecules that if you have a collision with the appropriate orientation that occurs, that it would react. So therefore, the reaction rate is proportional to the proportion of molecules with energy greater than the activation energy. So this is the sufficient energy criterion written in terms of molecular speeds. Now, what if we have a higher temperature? As we saw before with molecular speeds, essentially, when you have a higher temperature, you have a lower peak and it's shifted towards the right. So this is T2, which is greater than T1. At this higher temperature, you see that this area with energy greater than the activation energy, the area I'm scribbling over right now, this proportion increases, and hence the reaction rate increases with an increase in temperature. It turns out that this proportion, this probability, the probability of having a molecule with energy greater than the activation energy is given by the exponential factor e to the minus EA over RT, where EA is the activation energy, that's in joules per mole, and R is 8.314 joules per mole per Kelvin. The temperature, of course, must be in kelvins.